This video is for week 5's digital multimedia content based on model 1. The first thing you need to learn is what's the data and what's the difference between data and information. Data refers to the symbols that represent people, events, things, and ideas. Data is raw, unorganized facts that need to be processed. Data can be something simple and seemingly random and useless until it is organized. When data is processed, organized, structured, or presented in a given context so as to make it useful, it is called information. For example, each student's test score is one piece of data. Your quiz one's grade is one piece of data. The average score of a class is information that can be derived from the given data. Data becomes information when it is presented in a format that people can understand and use. Data representations refers to the form in which data is stored, processed, and transmitted. Today, digital data representation has replaced the analog method previously used for storing and transmitting photos, videos, and text. Digital data is text, numbers, graphics, sound, and video that have been converted into discrete digits such as 0 and 1. In contrast, analog data is represented using an infinity scales of value. The process of converting text, number, photo, or music into digital data that can be manipulated by electronic device is called digitalization. The 0 and 1 used to represent digital data are referred to as binary digits. It is from this term that we get the word bit, B-I-T, binary digits. A bit is a 0 or 1 used in the digital representation of data. A digital file, usually referred to simply as a file, is a named collection of data that exists on a storage media such as a hard disk, CD, DVD, or flash drive. Digital signal can take many forms except binary digits such as voltage variations, light and dark spots, magnetized particles. Numerical data here consists of numbers that can be used in arithmetic operations, can be used in mathematical calculations. For example, your annual income is numerical data. But not every data that has number is numerical data. Your social security number, your telephone number, your street number, and similar data are not represented by numerical data. So they are called numerals. They are not considered as numerical data because they are never used in mathematical calculation. So this is the most important characteristics of numerical data. So it must make sense to be used in mathematical calculation. It does not make sense to use your social security number to multiply by something, right? So your social security number, your phone number, although they both have numbers, they are numericals. They are not. They are numerous. Sorry, they are not numerical data. The digital device represents numerical data using the binary number system, also called base 2. The binary number system only have two digits, either 0 or 1. no numerals like 2 exists in the system. So the number 2 is represented in binary as 110. So let me do a little bit explanation about base 2 here. So when you are counting from 1 to 10 in the familiar decimal system, after reaching 9, you basically run out of digits, right? For 10, you have to use the digit 10. 0 is a placeholder and 1 indicates one group of tens. In binary, it is the same thing. You just run out of the digits sooner, right after you count to 1. To get to the next number, you use 0 as a placeholder and 1 indicates one group of 2's. In binary, then you count 0, 1, 1, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1 instead of counting 1, 2, 3, 4, 5, 6 in decimal. So you can refer to this figure 1, 2 for comparison between base 10 and base 2, between decimal and binary systems. Okay, so this slide show you how to convert number from decimal to binary. This is also our question 11 in quiz 2. So I have listed all steps in the note part. First, you should write down the decimal number, of course. Here we have 47. And then divide the number by 2 and write down the result underneath. And also write down the remainder on the right hand side. This will be either 0 or 1 because you divide the original number by 2. And keep on doing the same thing. Divide the result of the division by 2 and again write down the remainder, this one. And keep on doing this until the result of a division is 0. And then read this column from bottom to the top. This number at the bottom is called the most significant bit, MSB. And this bit on the top is called the least significant bit, LSB. And you read this series of 1 and 0 in the remainder column from the bottom to the top. 1, 0, 1, 1, 1, 1. So this is a binary equivalent of the decimal number 47. So here question 11 is what's the binary equivalent for the number 26? So I don't want to do the exactly same number here. So let me do a 23. So first step, divide this number by 2 and division is 11, remainder is 2. And then divide 11 by 2, division is 5. Okay, here should be a 1, sorry. And remainder is 1. And divide 5 by 2, division is 2, remainder is 1. And divide division 2 here by 2. The new division is 1 and remainder is 0. And divide 1 by 2 and division is 0. This is we are reaching the end. And the remainder is 1. Okay, so this is the most significant bit. This is the least significant bit. So we have 10111. Binary is 23 in decimal. Okay, this is 1 plus 2 plus 4, it's 7, and this is 16. Okay, yeah, that's correct. So this is what you should do for question 11. Please do not just give me a binary number, because I know there are some online calculators can help you to achieve this number. You need to show me your calculation steps to let me know you really understand those steps. Okay, this slide 7 instead shows you how to convert number from binary to decimal. So you need to first, of course, write down the binary number, and then multiply the digits by the value of the placeholder, the 0 power of 2, first power of 2, second power of 2, third, fourth, fifth, sixth, seventh power of 2. So how do you find those value? You can refer to any power of 2 table. So in question 12, it asks you to find the decimal equivalent of 1101101. Okay, so again, I don't want to do the exactly same number. Let me do 1101110. Okay, so here this is actually the least significant bit. I should multiply it with what? With 0 power of 2, which is 1, and get a 0. And this one, I should multiply it with the first power of 2. It is 2, and the result is 2. This one, I should multiply it by the second power of 2, which is 4. Result is 4. This one, I should multiply it by the third power of 2, which is 8. Result is 8. This 0, I should multiply it with the fourth power of 2, which is 16, but I still get 0. This one, I should multiply it by the fifth power of 2, which is 32. I have 32 here. And the last one, this is the most significant bit, right? I should multiply it by the sixth power of 2, which is 64. Result is 64. So, and then I add those numbers together. 64 plus 32 plus 8 plus 4 plus 2. Okay, the result will be 96, 106. Okay, this is 110. Okay, so 1101110 in binary is 110 in decimal. Okay, this is what you should do to answer question 12. Okay, from here, I want to briefly mention how bits are used to represent text. So this is not required in reading. So I will just talk about some very important context briefly. So character data is composed of letters, symbols, and numerals that cannot be used in calculations. So actually, numerals are represented as characters, not represented as they're not represented as numbers. The digital device use several types of codes to represent character data, such as this ASK and extended ASK, Unicodes, and their variants. The ASK stands for American Standard Code for Information Interchange, requires 7 bits for each character. So for example, the uppercase letter A is represented as 150 and 1 in ASK code. So actually you can calculate the maximum number of code in ASK. So what if all those 7 bits are 1? So what's the total number you can get? It is actually 128. So the ASK could provide codes for 128 characters, including uppercase letters, lowercase letters, punctuation symbols, and numerals, like this. The extended ASK is a superset of ASK that use 8 bits for each character. So you can calculate what's the maximum number of codes the extended ASK have. What if you have 8 bits of A? That's actually, if we add those numbers one by one, the total number is 256. So using 8 bits instead of using 7 bits allows extended ASK to provide codes for in total 256 characters. The additional extended characters include box and other graphical symbols. The Unicode use 16 bits and could provide codes for 65,000 characters. The UTF-8 is a variable length coding schema that uses 7 bits for common ASCII characters, but use 16-bit Unicode as necessary. So you may take a look at, this is from figure 1.3. Take a look at the ASCII codes. Note here, there is a code for the space character in addition to codes for symbols, numerals, uppercase letters, and lowercase letters. So I have a question in quiz 2 here. So what's the first 3 bytes in ASCII? So are they for 10B or are they for 10 space? So remember, space is also a character in ASCII. So you may notice here in the question body it says like first three bytes, not first 3 bits. So what's the difference between bits and byte? Basically all of the data stored and transmitted by a digital device is encoded as bits. The word bit, a shortened for binary digit, can be further represented as a lowercase b. A group of 8 bits is called a byte and is usually represented as an uppercase b. So that's the reason. Here you can see in the answers is 1, 2, 3, 4, 5, 6, 8. There are 8 bits, right? So this is a byte. That's the reason why this question asks what are the first 3 bytes. First 3 bytes. In total, 24 bits. Kilo, mega, giga, tera, and similar terms are used to quantify digital data. But the kilo, mega, giga, tera, those terms are slightly different in the context of computer because they are based on base 2, not on base 10. For example, in common usage, kilo represents as K, means 1,000, right? And 50K means 50,000 for your annual income. But in the context of computer, 50K means 51,200. Why is this difference? Because in the decimal number system base 2, a kilo is 10th power of 2. So the result will be 124. In the decimal number system we use on a daily basis, the number 1000 is the 3rd power of 10, right? But in the context of computer, those kilos, mega, giga, tera, they are all based on base 2. So a kilo is 10th power of 2. A mega is 20th power of 2. A giga is 30th power of 2, and so on. So they are not based on 10. So there are slight difference between the contents of computer and our daily usage. As a general rule, use bits for data rates, such as internet connection speed and movie download speed, and use bytes for file size and storage capacity. For example, here 104 KB. Kilobyte is often used when referring to a size of a small computer file, such as size of a Word document. 56 kbps, kilobits per second, can be used for slow data rates such as 56 kbps dial-up connection. 50 mbps, megabit, is used for a faster data rates such as 50 megabits per second internet connection. 3.2 MB, 3.2 megabytes is typically used when referring to the size of a file containing photos and video. This is a regular file size for a photo usually. 100 gigabit is used for really fast network speed. 16 gigabyte is commonly used to refer to storage capacity, like the storage capacity of your flash drive. Data compression refers to any techniques that record the data in a file so that it contains fewer bits. Compression is commonly referred to as zipping. Many compression techniques exist. They can be divided into two categories: lossless and lossy. The lossless compression provides a way to compress data and then reconstitute it into its original state. Calc data and numerical data in documents and spreadsheets are compressed using lossless techniques so that the uncompressed data is exactly the same as the original data. For example, you compressed your personal website files into a zip file and submit it to me, and when I unzip it on my local computer, I will get exactly the same file as you have. Otherwise, I cannot grade your submissions, right? The lossy comparison instead will throw away some of the original data during the comparison process. After data is uncompressed, it is not exactly the same as the original. This type of comparison typically used for music, image, and video because the human eyes and human ears cannot detect minor changes. Later in this set of slides, you will see more about the comparison techniques used to reduce the size of music, image, and video files. On your desktop or laptop computers, the compression utility is accessed from the same screen used to manage files. You can compress data in a single file, or you can combine multiple files to a single zipped file that is reconstituted to the original file when unzipped. Compressed file usually have a .zip file extension at the end of the file name and represent with a special icon. But you can also see other file extensions of compressed file such as .gz, .pkg, .tar.gz. Mention some concepts in digital audio, especially how to calculate file size for uncompressed and compressed digital files. Digital audio is a system in which we store, record, and manipulate audio information in a computer system. Certain characteristics of an analogy sound wave, like the frequency and amplitudes, are converted to data computer software can read. This allows us to manage, edit, and range audio in a software-based context. The software is converted into data through a series of snapshot measurements or called samples. A sample is taken at a particular time in the audio wave for example, at those points. This information is then converted into digestible binary data. When recording a voice message on your phone, for example, the sound wave of your voice are sampled many times per second by an analogy to digital converter ADC. Those samples are converted into binary 1 and 0, which are stored in an audio file. Then when the audio file is played, a digital to analogy converter DAC transforms the digital bits into analogy sound wave and outputs them through speaker. The ADC makes thousands of measurements per second. If we can take tons of measurements extremely quickly with enough possible values, we can effectively use these snapshots to reconstruct the resolution and complexities of an analogy wave by DAC. The ADC takes those measurements at a speed called sample rate, measured in kilohertz. In most digital analogy way, you will find an adjustable sample rate in your audio preference. This controls the sample rate for audio. The most common sample rate you will see is 44.1 kilohertz or 44,100 samples per second. This is standard for most customer audio used for formats like CDs. Higher sample rate you have to capture snapshots in an analogy wave. Higher audio quality you will have later in data results. But of course, you will need larger storage space for your digital results too. Regardless of sampling rates, data audio file size can be reduced using audio compression techniques. Audio compression reduces the size of a sound file by removing bits that represent noise and sound that are beyond the frequency of normal hearing. Uncompressed audio consists of rare sound waves that have been captured and converted to digital format without any further processing. As a result, uncompressed audio files tend to be the most accurate but take up a lot of disk space. Some common uncompressed audio formats include WAV, waveform audio file format, AIFF, audio interchange file format, and BWF, broadcasting wave format. Sample rate, as I already mentioned, is the number of times the audio is sampled per second. Could range from 8 kilohertz, which will result in very low quality later in data audio, up to 192,000 hertz, which will result in very high quality later. Some common sample rates include 48 kilohertz, 88.2 kilohertz, 96 kilohertz. The bit deep here is a number of bits in every single sample. The most common bit dips are 16, 24, and 32. So here, this is how you can calculate an uncompressed audio file size in bytes, not in bit. So you should use bit rate, multiply the bit per second, multiply by sample rate, and multiply by number of channels you have. Usually it's either 1 or 2 or 4, and multiply by the duration, how many minutes you have for that uncompressed audio. And this is how many bits you will have for the file size, and then you divide it by 8, you will get how many bytes you have for this file. So for example, 1 minute WAF is an uncompressed audio format, right? With 44.1 kilohertz, this is a sample rate, and 32 bits, this is a bit deep. With 2 channels, this is the number of channels, will be 32 multiplied by 44.1K, or you can write down 1000, that's fine, multiply by 2 channels, and multiply by 60 seconds. So this is a total bit that file will have. This is a total byte that file will have, and you can either represent the megabyte in decimal or in binary. Both work. So how do you jump from here to here? You can refer to some online converters. Let me see. Okay, So here, megabytes, I think it is from decimal system. Okay, this is how many megabytes in decimal the file will have. And if you want to use a base of 2, actually that will be more accurate. This is the how many MB that file will have in binary number system. So both work for your answer in quiz 2. As long as you get the correct byte, I'm okay with what kind of base you use for megabyte or gigabyte. Okay, so let's take a look at question 13, I believe. Okay, so what's the file size for 2-minute 2-channel uncompressed audio if the bit depth is 16, sample rate is 96 kilohertz? So the sample rate is 96 kilohertz, and the bit depth is 16. Number of channel 2, duration 120 seconds, and this is how many bits you will have. Let me calculate it on my own phone. Okay, so that's this number. This is how many bits that file will have, and byte is this number divided by 8. And how many megabyte it will have on base 2? Okay, this number. Binary, and you could also use base 10. It's just 46.08. Okay, this is for question 13, the file size of an uncompressed audio. Of compression, loosey compression and lossless compression. Lossless compression compress the file in such a way that the original quality of the file are not lost at all. This comparison technique borrows quality from the zip algorithm while the redundant data is removed from the file, and the integrity of the important bits of data will be untouched. Lossy compression instead reduces the size of original audio file up to 10 times, so some audio data is lost in the process. So here are some common lossless audio formats, including FLAC, Fewer Lossless Audio Codes, WMA, Windows Media Audio, ARAC, Apple Lossless Audio Codes. So MP3 is, I think everyone should be familiar with this one. This is a Lucy audio format, and AAC, OGG, those two are not that popular these days. This is how you can calculate the file size for compressed audio, such as MP3. You should use bitrate multiplied by number of channels, multiplied by duration, how many seconds that file has, and this is how many bits that file has. Divided by 8, you can get how many bytes that file has. Here, bitrate is the number of bits per second encoded. It could range from 96 to 320 kilobits per second kbps. Here, please pay attention. This is kilobits, not kilobyte. For 1 minute MP3 at 129 kbps, file size will be, this is a bit rate multiplied by a number of channel only one, duration 60 seconds, and this is how many kilobits the file will have, and divided by 8, this is how many bytes this 1 minute MP3 will have. It is 960 kilobytes. And for question 14, what's the file size for 4 minutes MP3 at 320 kbps? So the bit rate is 320k. And there's only one channel. MP3 usually only has one channel. And this is the duration, 240 seconds. And this is how many kilobits the file will have. Divided by 8, this is how many kilobytes the file will have. The file will has, it is 9,600. Mention the bitmap graph and vector graph. When you take a photograph using a digital camera or scan an image from a magazine, you are creating a bitmap graph. Basically, it is a collection of grids where each individual square is a pixel that contains color information. The key characteristics are the number of pixels or squares in the grid and the amount of information in each square pixel. There are several bitmap file formats to choose from, and each has advantage and disadvantage. You've likely heard of or used some of these files here, like BMP, GIF, JPEG, EXIF, PNG, and TIFF. Windows exclusively use BMP. GIFs and JPEGs are designed for web transfer, and EXIF files come from digital camera and carry photo-specific information and camera setting. BMPs are large full files that cannot be compressed. Other formats like GIF, JPEG, and PNG use compression algorithms that make the files smaller and easier to upload and download via internet, making them extra convenient when working with online projects and designs. The size of the file is related directly with its quality. The higher the quality, the bigger the file, which can be tough if you want to use a high-quality bitmap image on the web. Unlike vector graph, which is scalable, you cannot scratch or enlarge bitmap images without sacrificing the quality. When you resize a bitmap graph, it tends to lose quality. Um, Bitmaps are perfect for creating detailed image like photographs because of the amount of data each pixel can have. The greater the amount of data, the broader the range of colors it can display, and it is much easier to create a colorful image with realistic color tones when you have access to a full range of colors. Uh, Also, when you are looking to edit or add effects to your image, bitmaps are the way to go. You can change the color profiles of individual pixels to affect the overall look of the entire image. Uh, for example, you can smooth lines, create a drop, shadow, and even um, change colors of the background and foreground simultaneously. You can create a bitmap graph from scratching using the tools provided by graphics software, specifically a category of graph software referred as printer softwares. Uh, you might be familiar with printer software such as Photoshop, Apple Photos, and Microsoft printers. You can also use a scanner to convert the printed image into a bitmap image. A scanner essentially divides image into a fine grade of cells and assigns a digital value for the color of each cell. As the scan progresses, these values are transferred to your digital device and stored as a bitmap image file there. In a digital camera, the lens focuses light from the image onto a small image sensor called the CCD, charge coupled device. This technology is used in standalone digital cameras and smartphone cameras. A CCD contains a grid of tiny uh, light sensitive diodes called photosite. The number of photosite depends on the size of the CCD. A CCD's photo size corresponds to pixels. The more pixels used to capture image, the higher its resolution and the better the resulting picture. You may still remember the HTML and CSS color part. Today's color display device represent color mainly using the RGB color model: green, red, green, blue. The color displayed for a pixel is based on the intensity of red, green, and blue signals received by the screen's color elements. Each red, green, and blue signals is assigned a value ranging from 0 to 255. 0 represents the absence of this color, and 255 represents the highest intensity level for that color. Uh, a, max, a pixel appears white if the red, green, and blue signals are set to maximum intensity. If red, green, and blue signals are equal but at a lower intensity, the pixel display a shadow of gray. A pixel appears violet if it receives high red and blue signals and just a bit of green. Color values can be specified in decimal, base 10, like this, or hexadecimal, base 16, like this, or base 2, binary, like this. So 8 bits for each color element, 3 bytes in total for a color. So here each RGB can have 256 values, right? 0 to 255. The number of possible color is 16.7 millions. You can use 265 multiplied by 265 and multiplied by 265. The number of color available in a graphic is referred to as color deep, with 8 bits used to represent each color value. One pixel requires 24 bits. Images that use 24 bits for each pixel have a color depth of 24. The 24-bit color depth is also called true color. The dimensions of the grids that forms a bitmap graph are referred to as image resolution. The resolution of a bitmap is usually expressed as the number of horizontal and vertical pixels it contains. For example, a small graphic for a web page might have a resolution of 150 multiplied by 100 pixels, which means 150 pixels across and 100 pixels height. High resolution graphics contain more data than low resolution graphics, of course. With more data, it is possible to display and print high quality image that are sharper and clearer than image produced using less data. The bitmap graph are resolution dependent because each element is a independent pixel. As you scratch the surface, the grid maintains the same number of horizontal and vertical cells, but each cell becomes larger, the grid becomes more visible, and the image develops an unwanted appearance referred to a pixelation. Simply scratching or enlarging a bitmap will not produce high quality result. Usually it will reduce the quality of that certain bitmap image. The graphic software offers option for changing the resolution of bitmap image. Suppose here you reduce the resolution from 2160 multiplied by 1440 to 1080 multiplied by 720. The image grid becomes a quarter of its original size. 1/3 multiplied by 1/3, that's a quarter. But every fourth pixel was removed from the image, which typically reduces image quality. If you attempt to enlarge a bitmap by increasing its resolution, your computer must somehow add pixels because no additional picture data exists. Most graphic software use a process called pixel interpolations to create new pixels by averaging the color of nearby pixels. For some image, pixel interpolations produce an enlargement that appears very similar to the original. But other images, particularly those with strong curved or lines, may not have that good results when you did a pixel interpolations. The minimum resolution for printed output is 72 pixel per inch. You can say 72 ppi. Suppose that a photo taken with a smartphone has a resolution like this. This is a width, this is a height. At 72 ppi, the photo can be printed up to a size of 26 multiplied by 36. to print the same photo, but with a better resolution of 150 ppi, just like this, the poster would be much smaller, about here 12 multiplied by 17. How can you check the size of the image of the document? You can use Photoshop to estimate the file size at certain resolution. Okay, so I think I have, yeah, I have Photoshop here. Okay, so this is this is a photo of Emily. So if I want to know what's the size for 72 ppi of this image, I can go to image size here, and now the resolution is 300. That's a very high resolution, and I can change it to 32. As you see, this is the width and the height for 32 ppi resolution, and this is image size. So if I want to send this picture to be printed, this is the minimum size this image should have. Okay, another type of graphic is called a vector graphic, vector image. This is an image made up of paths defined by a start and end point. Path here consists of basic shapes such as lines, polygons, and curves. Instead of storing the color value for each pixel, a vector graphs file contains instructions that a computer use to create the shapes, size, position, and color for each object in an image. So like this one, this example from our textbooks, this one means draw a line of width 3 beginning at coordinates 2020 and extends the line to coordinates 2060. Colored the line with this color. This is a green color. And this is another example from our textbooks. So you should be able to read this command. This is a starting point, 100, 100, width and height. This is a field color, also green. And this one is, oh, I'm sorry. This one is from our quiz 2, right? So this is a circle. The circle starting from points 100 and 100, the radius is 80, and this is a field color white, so this is basically a white circle. The border width is 10, and the border color is this one. Let me search to see what's this color. Okay, this is still green. Okay, so this is basically a white circle with a radius of 80 and with a green border that has a width of 10, right? So this is an example from our quiz 2. So this slide 23, summarizes the major difference between vector graphs and bitmap graphs. So bitmaps are made of pixels, while vector image are software created and based on mathematical calculations. It is made of shapes. The vector image are not restricted to an rectangular shape like bitmaps. Vector objects can be placed over other objects, and the objects below will show still. A vector circle and bitmap circle appear to be the same when seen on a white background. However, when a bitmap circle is placed over another color, it has a rectangular box around it from the white pixel in the image. The vector image also are generally smooth and more usable, and you can scale them fully without sacrificing quality. In general, vectors are for making scalable work files, while bitmaps are for making shareable final projects. Also, because bitmap bitmaps are resolution dependent, it is impossible to increase or decrease their size without sacrificing image quality. When you reduce the size of a bitmap image through your software, uh, it's like, for example, like it's in with its resize option, pixels must be discarded. The vector-based image instead are resolution independent because they are scalable. You can increase or decrease the size of the vector image to any degree, and the lines will remain shape both on screen and also in print. The vector objects are defined by mathematical equations, as I mentioned before, rather than pixels. So changing the abstract of a vector object does not affect the object itself. You can fully change any number of object attributes without destroying the basic object. An object can be modified by changing its attributes and by shaping and transforming its using nodes and control handles. In practice, vector images are unsuitable for producing photorealistic images. That's why most vector images tend to have a cartoon-like appearance. And finally, the vector image primarily originates from the software. So you cannot create vector image using smartphone unless you have some software on a smartphone, using smartphone or using your digital camera. Also, you cannot scan an image and save it as a vector file without using any special convention software. So those are some common softwares and file formats of vector graphs. Those are some examples I already mentioned for the bitmap images. Week 5 is digital video. Digital video is a type of motion graphics that use bits to store color and brightness data for each video frame. Each bitmap image is referred to as a frame. The process of creating digital video is similar to storing the data for a series of bitmap images, in which a color for each pixel is represented by a binary number. The number of frames that are displayed per second is called the frame rate. Higher frame rate produce video that more smoothly simulates real motion. So basically, higher frame rates you have, higher quality the video is. A video with a frame size of, for example, 640 multiplied by 480 will fit the screen of a device that have a similar screen size, mapping each pixel in the video frame to each pixel on the screen. Scratching the video to fit a larger screen requires pixel interpolations, which tends to reduce the quality of the video. So if you have a larger frame size, but you want to play it in a small screen, the video will still be played. So just vice versa, if you want to play a small frame size video on a large size screen, then the projector will need to do pixel interpolations. The video resolution can be expressed as width multiplied by height, as the horizontal resolution, or as the vertical resolution. A resolution of, for example, 1920 multiplied by 1080 can also be expressed using its vertical resolution as 180p. The P here means progressive scan, in which the frame is drawn line by line in sequence from the top of the image to the bottom. An interline scan instead uses a different scanning technique that produces the image by drawing every other line and then going back and filling in the in-between lines. Digital video for computers typically use progressive scans, while digital television use interline scanning. Aspect ratio is a proportional relation between the width and height of image or video frame. Here 4:3 was a standard aspect ratio for television and old movies, earlier digital videos, first generation of personal computers and iPad. Today's widescreen devices such as laptops and smartphones are designed for the 16:9 aspect ratio, which is recommended for most modern videos, including those uploaded to YouTube. When a 3:4 video is displayed in a widescreen player like this, they are bordered by the black bars of a letterbox. As long as the proportion of horizontal and vertical pixels remains the same, the aspect ratio is consistent. For example, a video frame with 1280 multiplied by 720 resolution has an aspect ratio of 16:9, as does a video with a resolution of 3840 multiplied by 2160. Both videos fit in a widescreen playback window, but a video with higher resolution offers a sharper, higher quality image. Divides the horizontal by the vertical resolution. You can find the aspect ratio. If the result is 1.7, then the aspect ratio is 16 to 9. If the result is 1.3, this, then the aspect ratio is 4 to 3. The comparison ratio produce the best quality video is 2 to 1. Okay, this is last slide. Well, it will show you how to calculate file size for uncompressed video. So you need to use bit rate multiplied by time, by duration. And then how to calculate the bit rate. Bit rate is the number of bits that are processed during a specific unit of time, usually in 1 second. A bit rate is resolution multiplied by color depth multiplied by frame rate. So yeah, let me just show you an example. So this is a resolution like this, and the color depth is 24, and the frame rate is also 24, and this is how many bits you will need to store a 1 second video with this bit rate. So then a 1 minute uncompressed video file size with this bit rate is how many bits here multiplied by duration multiplied by 60 seconds, and you can convert this number to gigabytes either on the base of 10 or on the base of 2. So I can show you how to do this. Yeah, I have seen this before. So it's a gigabyte. This is based on decimal. Oh, I need to divide this number with 8 first. Okay, so if you use a decimal system, this is how many gigabytes you will have for 1 minute uncompressed video file with this resolution with 24 color depth with 24 FPS. And if you want to use a if you want to use a binary system, this is the how many gigabyte you need to have. So in quiz 2, this is a question. The solution is (640) multiplied by 480, and color depth is 16, FPS is 30. So this is a bit rate you will have. And for 1 minute, uncompressed video of this bit rate, you use this number, multiply by 60. You can just use a bit to represent your answer. That's fine. Or you can convert it into gigabyte. This is how many gigabytes you will need based on binary, and this is how many gigabyte you will need based on decimal. Either is fine, as long as you know the calculation steps. Okay, so I think that's all for week 5 slides. If you have any questions, you're welcome to give me an email. Thank you. Here I will talk about the HTML and CSS layout. A web page is often divided into different parts like a magazine or newspaper. How do you achieve such layout in website? In website design is to use related HTML and CSS page layout techniques. Those techniques allow you to take elements contained in a web page and control where they are positioned relative to their default position in normal layout flow, the other elements around them, their parent container, and the main viewport, the main window. This is an example of a normal layout flow. Normal layout flow is how the browser lays out HTML pages by default when you do nothing to control page layout. Note here how the HTML is displayed in the exact order in which it appears in the source code, with elements stacked up on top of one another. The first paragraph followed by the unordered list, followed by second paragraph. Having no layout is okay if all you want is one big column of content. However, if a user makes the browser window really wide, it gets kind of annoying to read. After each line, your eyes have a long distance to travel right to left to the next line. When you use CSS to create layout, you are moving the element away from the normal layout flow. There are several approaches you can use to create layouts. The first one is called HTML tables. So you can add content to each table cell to kind of organize those content, but this one is not recommended. We will mainly talk about the CSS float property method with divs or HTML5 semantic elements. There are several other approaches you can use to create HTML CSS layout, including CSS Flexbox, CSS framework, CSS grades. Those are not required for this class, so I have attached the link here. You can take a look if you are interested in those content. Div side, I think you should still remember. Divs are building blocks of multi-section layout. We have seen the div element in week 3. A div element is a block level element that always starts on a new line and takes up the full width available. It can be used to divide the page into logical sections and can hold whatever you need inside it. You can have blocks of text, image, or other elements in divs and then put them together in a layout. Of course, you need to also position those those divs in a reasonable order. This is a typical div-based layout. The main div is called page, and then you have header, you have navigation, you have content, the sidebar, and the footer. Like this. As you can see, most of the divs here are associated with ID because it's highly likely you only have one header, one sidebar, one footer, one content box. So content box you may have more than one in a certain web page, but those two divs are associated with class activities because you may have more than one activities in a single page. So be sure you know the difference from ID style and class style in CSS. The div tag, the div element itself only has one associated attribute, which is alignment. Other formats of a div must be defined using the style sheet using CSS. This is an example of how to create a very simple navigation div. First, in the CSS part, in the external CSS file, you define a top navigation bar ID style. This is the width of the navigation bar, background color, and padding. And then in the HTML file, you call this top navigation ID style. And this is the first link in the navigation bar to another page, to the same page actually. This is another link to the about page in the navigation bar. This time, since you only have one web page in your assignments, you don't need to create a navigation bar since you don't have different pages. Before the HTML5 was released, if you want to create div-based layouts like this, you need to divide divs one by one. HTML5 offers some semantic element to give some divs specific names so you can use them directly. There are 6 semantic elements you can use, which means you can define style with those names in your CSS. You don't need to define them as a class or ID. You don't need that hashtag or the dots in front of those HTML elements. Here, header is used to define the header information on the page. Typically, the header is repeated on every page of a site, although that is not required. And section navigation is used to define a container of navigation links. You don't need to do that for your assignment. And section defines a generic content or application section. Examples of sections will be book chapters or the named section of a thesis. A site's homepage could be split into sections such as introductions, news, and content information. A section begins with a heading such as H1, followed by other content. A general rule is to use section if the area being defined would be included in an outline of the document or page. Article is used to define a block of text that represents a single article, story, or message. An article can be distinguished from other text in that it can be logically stand alone. For example, when on a news side, each news story is an independent article. A side, this is similar to a sidebar. The function is used to define a block of text that is separated from the main discussion, such as a note, a tip. An aside can be distinguished from other texts in that it could be pulled out and discarded without disrupting the main document in which it appears. The footer is used to define the text at the bottom of a page, such as the copyright or contact information. Again, it is typically repeated on every page of a site. If you use semantic text to structure your page and someone views it with a browser that does not support HTML5, then the browser will ignore the text. It does not understand. So I guess your HTML page will looks very strange because you will lose all layouts you design. So this is an example of a layout with HTML5 semantic elements. So here you can see it uses header, navigation, aside, footer, articles directly. You don't need to define them as an ID style, class style anymore. But for the paper and content, here they are still defined as an ID style because page and content are not HTML5 semantic elements. So you can use either HTML5 semantic element, or you can use like an ordinary div with predefined ID or class style in your CSS. Both ways work. My only requirement is you must be consistent. So here, this is my copy. So here footer, I use it as HTML5 element, so I do not divide it as a class style or ID style. And so does section, so does header. But I define two sidebar styles here as ID styles. And I define a container class and a center class. So in my HTML code, let me see. Okay, all of them works. All of them work. So what I'm trying to say is you can either use such a layout with all HTML5 semantic elements, or you can use a layout like this with predefined ID class and ID style and class style. I'm sorry. But especially if you use the predefined ID style and class style, be sure you call their name correctly in your HTML code. From here, I will finish the remaining parts of week 4 HTML and CSS layout. I will start from how to position divs. Since divs are block level elements, they default to 100% of the available screen width and add line breaks between each other. They will all just stack up underneath one another unless you position them in some way. In other words, you need to define position for each div. There are two ways of position a certain div. You can use float style rules. You can also use the position style rules. You will see examples for both. The simplest way to position div is to use the CSS float property. You can float any element left or right, and it will align itself over to the side of whatever element it is contented with. Floating element takes a little bit of practice, especially if the columns, the height of each div are not the same height. But it can result in many traditional and non-traditional layout. Okay, this is how you can float this image to the right. If I change the value to left, you can see now the image floats left. So when you use the float property, you should also use the width property to indicate how wide the floated image should be. If you don't, result can be inconsistent, but the box is likely to take up the full width of the containing elements, just like it would in normal flow. So this is a float left effect. You can see if I do not have the inline style, you can see the height of the image and the height of the text are not the same. So if you do not define the width and the height, the effect is not good. So let's put it here. With height and margin right, which means there should be some space between this image and the text. Okay, looks better, right? You can use the clear property to specify what elements can flow besides the cleared elements and on which side. So here is an example. Okay, so the value of clear could be non-left right both and inherent. If the value is left, that means no floating elements allowed on the left side of that element. If the value is right, then no floating elements allowed on the right side of that element. If the value is both, it means no floating elements allowed on either side, either the left or the right side. So we can take a look at the example here. So the first div do not have clear, second do not, third do not. Okay, this div 4 have a clear value left, which means no other element can appear on the left side of this div 4. So if we do not have this clear, you can see this div 4 is stacked on top of div 3. But if you have the clear left, that means no divs, no other element can touch the left side of div 4. So div 4 has been moved to the button. And if I change the value to, let me see, right, So the effect is the same as without clear because still no other element touch the right side of div 4. But if I have the value as both, the effect will be the same as if I have clear value left. To create column layout, you can simply float all of the column divisions to the same side, and they will line up beside each other as long as they fit. You can also give each column specific width in px or percentage, margins, the gaps between the columns, and paddings. You can refer to darkest text box for HTML and CSS codes fixed with layout and liquid layout. Another way to position div is to use the position property. In normal layout flow, each block level element sits on top of the next one. Since this is the default way in which browser treat HTML elements, you don't need a CSS property to indicate that element should appear in normal flow. But if you do want to emphasize that, you can use position static. This means an element will be placed in normal HTML layout flow. And this position property has some other values like relatives, absolute, fixed. We don't use the sticky very often. So here the relative position moves an element in relation to where it would have been in normal flow. For example, you can move an element div 10 pixels lower than it would have been in normal flow or 20% to the right. You can indicate that an element should be relatively positioned using the position property with a value of relative. You then use the offset properties top, bottom, left, right to indicate how far to move the element from where it would have been in normal flow. So here the position value is relative, left is 30 pixel, and I can change it to 50. You can see I have more space here. I can change it to top. Okay, I have more space here between paragraph and this div. Can change it to right. Okay, you can see I have 50 pixel with space here. So basically, to move the element, the div up or down, you can use either the top or bottom properties. To move the box horizontally, you can use either left or right properties. Remember, the reference of this position is its neighbor element. So in this case, is this paragraph. And for absolute position, if the position property is giving a value of absolute, the HTML element is taken out of normal flow and no longer affects the position of other elements on the page. They act like it is not there. The box offset property top, bottom, left, right specify where the element should appear in relation to its containing element. If an absolute positioned element has no positioned parents, it uses the document body. because this is a relative div, the parent div, and then this is the absolute div. Let me change top to 100. I can also change the button to 100. Okay, so in this case, the reference for this absolute position div is its parent div, is this relative div. Fixed position is a type of absolute position that requires a position property to have a value fixed. It positions the element in relation to the web browser window. Therefore, when a user scrolls down the page, it stays in the exact same place. The top right button and left properties are used to position the element. Compared to absolute, the reference is the view part, while absolute is the nearest position parent. Take a look at this one. Position fixed. This div has a position fixed. So the reference is the web browser window. So I cannot scroll down this page, but basically this div will stay there no matter how you move the web browser window. And finally, the z-index. The z-index property specifies the stack order of an element, which element should be placed in front of or behind the others. An element can have a positive or negative stack order. This is a z-index. So you can see here, this image has a z-index value -1. So this image has to be placed behind the text, right? If I change it to 1, it is now in front of the text, because the default value of the index will be 0. So now this the index of the image has a priority, so it has to be bring to the front. Okay, so this slide shows some other effects for CSS image. You can refer to examples here to see how to make rounded images, circled images, basically by changing the value of border radius. How to create responsive images, how to center image. Okay, background image. So you need to have a background image or background color in your personal website assignment. The background image property will allow you to place image behind any HTML elements. This could be an entire image, or just a entire page, or just a part of the page. By default, a background image is placed at the top left corner of an element and repeated both vertically and horizontally. So you can have more than one background image together on one page. So you should also set a background color for the body in case the background image cannot be shown. This is a good practice. Okay, so you may see there are some other properties here. So background repeat property. This one sets if or how a background image will be repeated. By default, a background image is repeated both vertically and horizontally. The background image is placed according to the background position property, this one. And the background attachment property is used to set whether a background image scrolls with the rest of the page or it is fixed. So I will show them one by one. There are several values of background repeat. The default one is repeat, then the background image will be repeated both vertically and horizontally. You can also set a value as repeat X, which means the background image is repeated only horizontally. And if you set a value as no repeat, then the background image is not repeat. So this is a result of repeat X. This is a result of no repeat. So you only have like a one background image here, not for the entire page. Background position sets the starting point of a background image. By default, a background image will be placed at the top left corner of an element and repeated both vertically and horizontally. And the other value could be, you could use left top, left center, left bottom, or you can use a percentage. So the first value is the horizontal position, and the second value is the vertical. The top left is 0%, 0%. And you can also use XPOS, YPOS. Let's take a look at. Okay. Starting position left top, center, bottom right. And this is a 50-50. This is 25%, 35%. 10 pixel, 200 pixel. 50 pixel, 50 pixel. And background attachment is used to set whether a background image will scroll with the rest of the page or it will be fixed. The value could be scroll, fixed, local, initial, inherent. We will mainly use the first two. So if the background attachment value is scroll, then the background image will scroll with the page. So you can see when I scroll down, I cannot see the background image page, right? So it has a relative position. But if I have the value as fixed, you can see although I also scroll down the page, this background image is always there. It has an absolute position. You can also use a shorthand property called background to set background for a div or for the body. So some common properties you should have in the background color in case your background image cannot be shown. Background image, you must specify the image path. Well, what's the location of the image? Background repeat, attachment, and background position. Okay, the following 3 slides will show you how to add video and audio to your website. It is very similar to how you can add image to your site. So video tag opening, video tag closing, video tag, and SRC is for the file path of the video. Where is the location of the video? What's the location of the video? And here you can see the attributes associated with the video tag. If it's autoplay, the height, if the video content will be looped. And you can also use the source tag to embed more than one source of a video. So here it means you can use source to embed different file formats, different video file formats for a certain video. It's not like you can add more than one different videos inside of one video tag. So if you want to add more than one different videos, then you should use multiple video tags. This source tag is used in case your user's browser cannot play some video file formats. So then you use this source tag to include different video file formats for a certain same video. So as you can see here, this is my example. The video file names are actually the same, which means they're actually the same video, but they are in different video file formats. Similarly, this is how you can add audios. Opening audio tag, closing audio tag, and the audio path. What's the location of the audio? You can also use the source tag to embed different audio file formats for the same audio. So those are not different audios. They are the same audio, but just they are in different file formats. Okay, so our video and audio tags are new HTML elements in HTML5. So if you want to play video audio in old browsers, you want your user to be able to play video this in old browser, you can use the embed tag. So this is the path of the video types, width, height, and those are some other attributes. If the video allows scrapped access, if it allows full screens. So you can take a look at WinPen's textbook from page 279 to page 283 for how to insert video audios for HTML5 for those web browsers that can read HTML5 code, or for those web browsers that cannot read HTML5 code. Okay, so that's all for the remaining parts of week 4. Thank you.